Okay, so let's start. Do you have any questions from last times? Okay, so today I want to continue about spaces of conformal blocks, degenerate fields, and then maybe about KZ equation and some quasi-classical limits of these equations. So first, let us continue the discussion from the end on the last time about the fusion roles of conformal blocks. We studied the following situation when we have a space of conformal blocks of this kind, so some alpha infinity, alpha 1, phi to 1, phi to 1, and it was alpha 0, and this space of conformal blocks was isomorphic to a direct sum for conformal blocks of this kind. Doesn't matter to use to write not fields but their charges. So, and here it was alpha 3 1. Yeah, I was writing this as a tensor product. Oh, let me. Yes, so it should be enough. At the beginning, I didn't know that one can take choke the entrance, and I'm still forgetting to do this. Yeah, it was counterintuitive. So I also was in such situation many times. So there is such a sum, and we computed originally that dimension of this space is 4, and so the dimension of this space was 3, and let me think. Oh, actually, Wait, it was at the end uh, of a lecture, and uh, mm, oh, maybe there was. Mm, so it was probably. So if I wrote this correctly, there should be a formal block with more fields, something like this. Alpha 1, and this degenerate fields are external, or not external, but some additional fields. Mm, so, mm, wait, what am I doing? Oh no, it was fine. It's that I forgot to write to add 1 point on the right? So it should be alpha 1, and here it should also be alpha 1. So here dimension is 1, since it is just an identity operator. Uh, and the question is, what kind of conformal blocks do we have here? Like, what is the basis in this three-dimensional space? What do you think? So it is uh, alpha 3, 1. This is alpha 0. This is alpha 1. And this is alpha infinity. So what are possible values of this intermediate charge? Hmm? No, no. Mm, it is so if there is no such field, then these values will be alpha 0, alpha 1, alpha infinity. But originally, originally we had something like this. We had alpha infinity, uh, alpha. Oh, sorry, it was alpha 1, alpha 0, and this was alpha to 1, and this was alpha to 1. So what were possible options for this charge and for this charge? So I can remind on the formula for alpha and m. Mm-hmm. So let me write some epsilon b over 2, and the next one. Yes, yes, because when we look at this part of conformal block, we can simply forget about the internal structure of this and use only the fact that there are two Rama modules, not Rama modules, but this. No, if alpha is general, there are Rama modules with such charges, and then we do the same procedure with another generate field. So this is alpha 0 plus epsilon b over 2 plus epsilon prime b over 2. So it is uh, uh, alpha 0 plus b, alpha 0 minus b, uh, alpha 0, right? For such values. And now we say that conformal blocks of this kind mm, isomorphic to conformal blocks of this kind. So alpha infinity, alpha 0, alpha 1, and alpha to 1, alpha to 1. And here we have two options. It is still four-dimensional space, but it is split in a different way. So one option is when this alpha is 0, then this charge that corresponds to this leg on the left should be 0. Right? And this corresponds to such conformal block. And what are the other three? So one conformal block so we can we can write a basis in the space of conformal blocks. So these legs are all alpha to 1. And possible values of alpha 0 are alpha 0, let's put it plus b, alpha 0, alpha 0 minus b, and here it is just alpha 0. So alpha 0 appears twice. And the question is, what can be on this leg? So we clearly have one conformal block with identity operator here. And this identity operator does not change alpha 0. So it's 1 vector in the space. But here, the only option is to have alpha 3 1 3 times.
Wouldn't alpha 3 1 shift the weight by plus minus b?
Well, plus minus b and 0, because who else can do this? We have only two options. Either it is identity operator or alpha 3 1. So the space of conformal blocks with identity operator is one-dimensional, because whatever field multiplied by 1, it stays the same field. So we cannot find a second such conformal block with alpha equal to 0 in this channel. So all other conformal blocks can only contain alpha 3 1. So is it fine? Yeah. So mm, uh, yes, so this way we can conclude that there is at least, so there are the following fusion rules. So fusion rules is something that is similar to the tensor product of representations, but it's not a tensor product, because naive tensor product shifts central charge. It can make C equals to 2 from C equals to 2C from just C. So it will be a tensor product of representations, but it is not what is happening here. So fusion rules describe which describe non-trivial channels in the conformal blocks. In a sense, if you know that the only non-trivial conformal blocks are with alpha shifted by b by plus minus b over 2, then it means that fusion rules of phi to 1 let me write it. So phi to 1 with the alpha is the alpha plus b over 2 plus the alpha minus b over 2. So in particular, phi to 1 with phi to 1 with itself is identity operator plus phi 3 1. And then finally, phi 3 1 with the alpha is the sum over n equals to minus 1 0 1 v alpha plus bn, right? Actually, I can still use this part of Blackboard. And let us now try to think about the general case. So is it fine? So mm, so in,
So
hmm?
if I choose phi for the one with the alpha, will I get the sum over four terms?
Yes, yes, yes. And this is what I'm going to explain, and I'm thinking how to do this better. Mm. So we can simply do like this. So suppose that we have such a property for phi and 1. Uh, so uh, mm, uh, uh, maybe some phi k1. Suppose that we are studying the fusion rules of phi to 1 tensor phi k1 times v alpha. So it will be, we can write it one way. It will be 5 to 1 tensor direct sum from k equals to probably 1 minus, from n equals to 1 minus k over 2 to k minus 1 over 2 v alpha plus plus k bn. And when we multiply by phi to 1, sorry, if we try the brackets, it will be sum from uh, n equals to minus k over 2 to k over 2 of alpha plus bn, plus sum from minus k over 2 plus 1 to k over 2 minus 1.
So the sum goes up to
K over 2,
no, the first sum on the left.
k minus, it should be 1, k minus 1 over 2, k over 2 minus 1, where alpha was beyond. Uh, we can write it this way, but alternatively we can write it as phi k plus 1 1 1 plus phi k minus 1 1 tensor v alpha. and this second term corresponds to phi k minus 1 1 tensor v alpha, and we know this. It is kind of not base of induction, but a previous step of an induction. So this is phi k minus 1 1 tensor v alpha. And so we conclude that this remaining part can only be phi k plus 1. This is yes, the general rule is that the general rule is this, that phi k1 v alpha so this is essentially the rule of tensor multiplication of pseudo-representations. So this behave like Varm modules, and this behave like finite dimensional representations. And so on. But it was for the fields phi k1. Well, let us think about generic fields, and let us do it the same way. First, it is clear that if you multiply phi 1 m and by alpha, if you compute it in this field, and then it will be simply the same sum. N equals to 1 minus m over 2, m minus 1 over 2, v alpha plus b inverse n. So it's certainly the same argument. Now let us take product of two such fields, phi k1 tensor phi 1m. So tensor v alpha. So on one side it will be such a double sum from k equals to 1 minus from n equals to 1 minus k over 2 to k minus 1 over 2 from n prime something like this. And but on the other side, so this happens if we multiply them in this order. But we can also multiply them in the other order. First multiply the degenerate field and then multiply by V alpha. And if you multiply this degenerate fields, then we simply get phi phi km. So maybe it's a little bit tricky question why only this field and not all the other. Mm, is there such question or not actually?
It's like I have to decouple the
Hmm?
representation, and whenever I get the ones, it's like a singlet.
Yes. So, hmm? Yes. So there are representations of SO2. We can probably say that we will definitely have such kind of field with such a dimension because we have corresponding shifts on the right, but we don't have other fields for dimensional reasons. So. Hmm?
Adds up to the correct number of representation on the right side.
Mm-hmm. So we can write like this: that it is a tensor, it is a fusion of phi km with V alpha. So this k and m are dimensions of two representations of two different SO2s. So, SO2 tensor maybe plus SO2. So here we simply read on this formula. And since the number of terms in the right hand side equals to km, we can conclude that such field should have a singular vector at the level km, because its fusion rules are obtained from some order km restriction. Like this. Right. Okay, maybe that's all about this degenerate fields for now. Mm. Uh, 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 do you have any questions? So let us then go to the KZ case. Let us derive the KZ equation. So we have some finely algebra with this OP. Do you remember the formula for the energy momentum tensor? By the way, it's called Sugawara construction in this formula. Would say it probably. In a sense, how can we represent some energy momentum tensor that involves only generators of this algebra? Yes. So if we say that this metric is AB, then it is sum over I, but the square should be normally ordered. GA of Z, GA of Z, normal product. And there was some coefficient. The coefficient was 1 over 2k plus h check. It's a dual Cox number that connects a scalar product in the adjoint and in the fundamental representations. And this h check for SLN h check equals to n. So for example, for SO2, it is k plus 2. So, and now the question is what kind of primary fields of this algebra are we going to consider? And the natural answer is the following. So there is some zero mode algebra, which is simply this SLN, and we can induce from a representation of this algebra. In a sense, we can consider the fields that lie in some representation of this non-affine SLN. Which means that J A of Z with some phi I of W is T A I J over Z minus W phi J of W. So these fields phi j are transformed as a representation of SLN. maybe we can. Oh, well, let us simply think that it is SLN. It does not matter. Non-affine. So it is more or less clear that such fields are Virasoro primaries because if you take square of these g's, we'll only have a second order pole. But now let us study this in more detail. For example, let us try to compute their dimension. So this formula is equivalent to a requirement that J JA 0 acting on such states phi I is TA ij sum over j phi j. TA are matrices in this representation. Let us maybe add some label of representation. In representation R of this SLN. And maybe we should also add this index R to these fields. Mm. So this phi R's of W are Virasoro primaries. And to check this, we need to write some explicit expansion for T of Z. Right? So let us remember what it is. Maybe we can write this formula again. That T of Z is the integral around Z dw over 2 pi I j of w j of Z w minus Z so and all this is ideally ordered. So it is the integral for absolute value of w is greater than absolute value of Z. W j of Z. So and here we have 1 over w plus Z over w squared plus Z squared over w cubed plus and so on. Minus the integral, no, no, alright, like plus the integral value of w less than absolute value of Z. 1 over z plus double over z squared plus double z squared over z cubed plus and so on. So it is j of this is j minus of z, j of z plus j of z, j plus of z, and in terms of modes, it is so the first mode here is j0 over z plus j wait. No, it starts from the constant term. Sorry, so it is j minus 1, simply j minus 1, plus j minus 2, z plus j minus 3 z squared plus and so on. Okay, it's simply j of z plus j of z, j0 over z plus j1 over z squared plus j2 over z cubed plus and so on. Right? So it is our German tensor, and it is a sum of ln over z to n plus 2. So if you want to check that such fields that form a representation of the finite algebra are also primaries, then we need to check the action of L1 and L2. So let us write, and we also need to compute the dimensions. So let us compute. L1 is what? Well, we are going to compute not just L1, but its action on phi I r. And L1 is in the coefficient in front of 1 over z to 1 over z cubed. So in this term, we can only take j0 and here we can only take j0 and j1. So from here j0, from here j1. So it will be something like j1 and j0. And it acts by 0 immediately. And here it is even worse because the first term is regular, j minus 1, so we should take j2 from this term. So it is mm, j minus 1, j2, and plus something. All this acts by 0. Is it clear? And if you want to act with L2, then it even worse. Because if you want this to act not by 0, we can only take j0, but then we need to take j2 from the next term. j2, j0 in this expression. Here we can only take product of something negative times something positive with big index. J minus 1, j3, for example, plus and so on. All this acts by 0. Right? So it's actually Versor prime A. And it's more or less the same argument that its OP with an energy momentum tensor starts only from the second order pole, because the original OP with G contained only the first order pole. And this fancy regular products does not change, don't change this situation. The recording. Let us finally compute the action. Actually, I forgot. Well, let me write like this. I forgot this prefactor. 2 times k plus h check. Let us act by L0. What are the terms that survive in this action? Actually, I omitted.
J0 and Z and times J0.
Well, it is also over, yes. Actually, I was omitting this algebra index, but it should be there. So maybe let me recover it. Sum over A. Oh, let me simply write like this. A. Uh, well, I can give you maybe some small piece because otherwise we can run out of talk. So, have this. There are these indices here. And we need to sum over repeating index. So and this is sum over A, and J A is 0, J is 0 squared, acting on this field. But if you look here, we realize that it is precisely the action of our finite algebra. So we can write this as sum over A if phi T A I T A J well, L T A sum over A and L let me just write some indices. Okay, it will be phi J T I T A J L presentation here. So it should probably be like this. So but now what is this? It is Casimir. Right? So it is C yes, C R I J quadratic Casimir phi J R. And since Casimir it acts diagonally, so it is simply CR phi I R. So therefore L0 acting on this field is CR over 2k plus h check times phi IR. So delta equals to CR over 2k plus h check. And let us think about the SO2 case. Actually, it's a good question what precisely to call Casimir. Probably the correct way to denote it is to say that it is 2 times Casimir. Because in this way we will have this familiar formula with j in j plus j plus 1. maybe. So example. We have a SO2. We have so SO2 at the level 1. And a fundamental representation. So in general, delta of delta corresponds to field of spin J will be J J plus 1 over K plus 2. And if you substitute K equals to 1, J equals to 1/2, then delta 1/2 delta will equal to 1/4. And do you remember such fields that had dimension 1/4? So do you remember this K equals 1 representation of SO2 had? How was it realized? Well, it was a one representation, and it is somehow related, but it was also Buzanized version. Oh, so we had a presentation of this algebra, which was E2 plus minus I square root of 2 phi, and J0 equals to I d phi with or without square root of 2. Maybe I square root of 2 d phi. And so this was about the about this affine Lie algebra, but we also studied its bosonic representations, and there were two examples. And one was this. This was 0 square root of 2 minus square root of 2 and so on. Like 2 square root of 2 minus 2 square root of 2. And here representation the highest level is trivial. But there was also another example, which was also caused under the action of this algebra. It was this. Minus 1 over square root of 2 and plus 1 over square root of 2. So it was two-dimensional. It was two-dimensional, precisely as we want. And then there is 3 over square root of 2 minus 3 over square root of 2, but we don't care about these representations. Sorry, like this. So here we have literally the dimensions. Delta equals to 1/4. So there are these two vertex operators with plus and minus 1 over square root of 2. This is the dimension. And also, this dimension coincides with dimension of to one field in C equals 1 CFT. Because let us remember all these formulas. So C equals to 1 plus 6 q squared, q equals to b plus b inverse, delta equals, so delta equals alpha times q minus alpha, alpha and m equals to 1 minus n over 2 plus 1 minus m over 2 b inverse. So let us substitute b. So we want c equals to 1, which means that b is I, and q equals to 0, of course. Alpha to 1 equals to minus, oh, sorry, it will be minus I over 2, delta to 1 equals to 1 quarter on the same field. And by the way, there is also some, so it will look like some kind of numerology, but let me write it anyway, because there are these formulas for Garasora, and there is this formula for the central charge of Gatmodia algebra. And by the way, what is this formula? Do you remember? C SO2. So for example, for SO2 hat, so what is the central charge C of K? Do you remember the formula? Maybe we can the formula for the energy momentum tensor. What kind of factors can we have here? Well, I think without 2, because it is silver 2 in the numerator of the OP. And what is in the numerator? So if k goes to infinity, it should be roughly the number of fields in the algebra. So well, it's SO2. So n equals to n equals to 3. So no, it's not n, it's a dimension of the algebra. So let us write it for SLN. So it will be k plus n, and here it will be n squared minus 1. All right. K times n squared minus 1. So, and if it is SO2 hat, then it will be 3 times k over k plus 2. Right? And people consider the following object. It is called coset construction. And we saw a simple example of this when we removed the U1 part from the algebra. So the idea was that if we have some subalgebra in our conformal algebra, we can consider everything that commutes with this algebra. And in particular, the energy momentum tensor of this object will be the difference of the energy momentum tensor of full algebra and of this subalgebra. It will commute with the subalgebra. And but this can be done also in the non-abelian case, when it is not so when it is not U1 but something less trivial. So we can consider the following coset. SO2 SO2 on the level k, tensor SO2 at the level 1 over SO2 on the level k plus 1. So the point is that this algebra is a subalgebra of this one, because we can simply take sum of generators within central charge k and with central charge 1, and this central extension, this second order term, will have coefficient k plus 1. So it is everything that commutes with this SO2. And let us compute a central charge of this coset. Let me call it CK. It will be what? It will be a sum of central of the two central charges of this algebras. So this central charge is 1. So 1 plus 3k over k plus 2 minus 3k over 3k plus 1 over k plus 3. So if we combine this together, we have k plus 2, k plus 3, row factor of 3. Here it is k plus 3 minus k plus 2, k plus 1. And I thought it should be coefficient 6 and not 3. I'm missing something.
Then we get the 2 from the numerator.
But where? Ah, oh, yeah, yes, precisely. Thanks. This 3 cancels with this. Yes. So, yes, it is fine. Yes. So it is minus 6, 6 divided by k plus 2, k plus 3. And 6. And if you try to write it in this way, we can rewrite it as 1 minus 6 let me 1 plus 6 square root of k plus 3 over k plus 2 minus I square root of k plus 2 over k plus 3. We have such kind of identity. And it's easy to understand because when we multiply them, we have square root of k plus 2, k plus 3 in the denominator, and we have k plus 3 minus k plus 2 in the numerator. So it's precisely this formula. So we see that this coincides with CFT with a central charge equals to with b squared equals to minus k plus 2 over k plus 3. Maybe or k plus, oh, here doesn't matter, k plus 2 over k plus 3. And CFTs with such central charges are called unitary minimal models. So, and in general, there are CFTs with central charge with b squared equals to minus p over q, and they are called all minimum models. I call them P or Q. So the advantage of this construction is that this way we can be sure that we obtain something unitary, because we start from unitary representations of SO2 hat, and something can be computed more explicitly. But actually, so it's a little bit far from the KZ equation. Do you have any questions about this? No, let us maybe go to the KZ equation. So that we have already computed the charge of this field. Maybe, or maybe it's so. So to obtain something on Kaggle, we need to compute the action of L minus 2 on this field, because L minus 1. L minus 1 acts as a derivative, and we can hope to derive some non-trivial equation this way. So let us compute on this. 2 times k plus h check L minus 1 on acting on phi I r. What would be? Which terms will survive in this formula?
J minus 1, J0.
Mm-hmm. Mm-hmm. Yes. So we have this. So this way, you see that L minus 1 acting on this state is sum over A, J A minus 1, uh, uh, times T A I J sum over A J I J R. So we can write that d phi I R of Z of W equals to what? So what will it be?
So you have also the k plus h2.
Ah, yeah, yes. Uh, how can we express this after the operator state correspondence? What in the what in this expression? Minus first mode times phi. This field has dimension 1, so minus first mode is the constant term in its OP around 0 or around some point.
Just get phi.
No, but this operator acts. How? How to express this action in terms of some OPEs or something of this kind? Of course, this sum over AJ, AIJ.
From the OP of j with phi, I can get another key.
But it's so T is so what part of J corresponds to this part with T? Which mode is this? Yes. So and this is the next mode. So J0 is here near 1 over Z. In this case, it will be 1 over Z, Z minus W. J1 is the constant term of expansion. What should it be? So, well, the question is essentially what is the vertex operator algebra map applied to uh, like this? How to express this in some terms? I can ask. I can also ask the following: what happens if we take the OP J of Z with phi JR of W? So what happens if we write all the terms of this OP? Like, what is this by definition?
Like we can write this, the modes like J, I, Z, phi, and
Who is J, Z, phi? Mm. I'm simply writing that it is a sum of J, A, N, phi, J, R of W over Z minus W to N plus 1. Or it is the same, it's a simply different way to write this sum over N, Z minus W to N plus 1. Is this clear? I simply write that OP of some current with the local field gives us the action of a mod of this current on this local field. Or this mod act on the space of fields, and this is this action. So, what should I write here? If I want to use some OPs to express this object.
J minus 1, phi.
Yes, but what is this? Well, I'm trying to write that it is the same as the regular product of J and phi. So it is dz over 2 pi I Z minus W J of Z, J of Z, phi JR of W. So and this integral is around W. So we take the OP of J of Z with phi R with phi J of W, and take the constant term in this OP, the term that corresponds to n minus 1 here. Yeah, so what should I write here now?
Okay, J, phi, J.
Well, in this integral, right? Because here it was some relation, you can think around 0, and now I move this relation to arbitrary point of the Riemann sphere. So I put this state at point W, and as well as this state. So the action this final algebra is the action on the space of operators at point W. And this action is defined by OPs. So we should simply take the OP of J of Z with phi of W and take its constant term, because in this corresponds to J minus 1. So it is the integral around W dz over 2 pi I Z minus W and J A of Z phi J R of W. So there is such a relation. So derivative of some field is expressed in terms of in terms of some OP with the current. Is it okay? And let us now try to apply this formula to some correlator that contains only fields of such kind. Oh, these representations in principle can be infinite dimensional. So there are different representations of SLN, not necessarily unitary. There are representations by vector fields acting on some forms. So there can be Avram modules of this SLNs. So we have different options, but all of them are representations of this finite dimensional algebra. So let us now consider the correlator of this form. Phi I phi I1 R1 of Z1 phi, and let us insert here the derivative d phi I1 of R1, and no, let us maybe write a correlator of this kind, In Rn of Zn. And let us call it psi of I1 In of Z1 Zn. And now let us compute the derivative of this psi in Z1. We can insert this formula and the correlator. Maybe it's better to compute derivative in k plus a check. It will be sum over a ta I1 j integral around z1 j a of z over 2 pi I z minus z1 so so here it's the regular part of this OP, but if we move this contour to all other points except Z1, this function becomes regular, and we will care only about a singular part of the OP, which is defined by this formula. So what will we get if we move this contour to all other points? So it will be sum over a ta I1 j sum over k different from 1. And what do we get if we compute this integral around some other point k? What in the residue of this expression? Hmm? Some L, for example.
All the other files that are not modified, let's set by k, which becomes by edit.
Mm-hmm. Yes, so it is mm, and what else?
And then I get the zk minus z1.
Yes, but it is with minus signs, so it will be 1 over z1 minus zk. Right? Because we move this contour to all other singularities. Oh. So we can raise this already. So this can be written as follows: k plus h check d zi of psi equals to sum over j different from I uh, omega ij over zi minus zj. Mm. And acting on psi. And this omega ij is a separate Casimir. Well, maybe it's bad notation. Mm, let me. So I was using ing for different things. Let's call it mn, and different from mn. So this omega mn is uh, sum over a t on m's tensor product on m's tensor factor. Tensor t on so t on n's tensor factor ta. So these are matrices of the action of our algebra on these sides m and n. So, is it fine?
So the index m is
Oh wait, It's let me call this L because we have n, which is the number of points. And L. Oh, so this index is the number of field. So there is a phi I m of ZM and phi I L of ZL. And this omega ml acts on this two fields in the product, mixing them. So, and these objects are called then Hamiltonians. Because it is because they can be interpreted as the interaction of some spin operators that act on different sides. So we can write that omega ml is so if it is a cell 2, we can write that this omega ml is a scalar product of spins acting on m sides and on l side. And if you consider the classical limiter, then we should consider some special asymptotics of psi. Namely, we should say that psi equals to e to 1 over k plus h check, or 1 over k plus h check some kind of action s that depends on z, some function. And it actually, so if I'm not wrong, it should be a Young functional on the Lagrange model. So psi is equal to this scalar factor times phi that has a limit, phi of z1, zn, and this phi, i1, in, and this one also has this indices. So if you substitute this into the KZ equation, and then this quasi-classical limit gives us derivatives of s on the left-hand side and actions of this Hamiltonians on the right-hand side. So we can call them we can call them HMs. So we will have something like dzi of s times phi equals to h BDZL HL actual on phi. So this phi in such limit becomes a Gadan wave function. But this is not the only limit, because so maybe let me say a few words uh, jumping to a little bit different topic. So in this case, this files correspond to so-called light degenerate fields. Oh, wait, I think. No, maybe here the distinction is different in this case. Yes, so I want to say that there is such limit, but there is also some option to consider different representations of mm, SO2, such that this matrices become that these generators become commuting matrices. So another option consider bigger representations of SO2. SO2, yeah, of SO2. So this looks this way. So we consider we choose some distinguished point Z1 and say that here we have, for example, two-dimensional representations. So here it is something two-dimensional. And in all other points, we have some representations of dimension much greater than one. So in this case, we can write this KZ equation for the first coordinate in the following way. So dz1 of psi equals to sum over m different from 1 t t1 tensor 1 over t plus h check times t a m. So, and we can say that these generators are new t checks. So they're new t's. So let us compute the commutator of such t's. So t a tilde m with t maybe actually here I tried to miss the two different limits. So it, it is strange. Or maybe there is some mistakes somewhere, but probably it is different. Classical limit probably it is. But the point is that if we put here k goes to infinity, uh, and uh, and then uh, so if you take k goes to infinity, then it will be, it becomes commutative algebra. But to make it some nice Poisson algebra, we should say that there is some Casimir, which is sum of T A and Casimir, which is sum of T A M T A M, and which now becomes 1 over k plus h check. Oh, it becomes k plus h check. Sum of ta tilde k plus hx squared. So if we want this to be some well-defined number, if we want t tildes to be some functions with a zero commutator but with some non-trivial Poisson bracket, then we need to ask this Casimir to grow like k plus a check squared. So this should become constant. And this, so the Casimir should grow quadratically. So it's uh, kind of how to get a Poisson algebra from some big representation of SO2 algebra. So and if you do like this, also I forgot to write this this expression z1 minus zm. So if you take this limit, then we will get a Fuchsian system. So if you take bigger representations of all psi's at if you take bigger representations of SO2 at all points except one, then this becomes not some equation on the multi-component vector, but on a two-component vector, which is a function of some tildes. So we can transform a part of this SO2 algebras into just Poisson algebras of functions. Yes. Are there any questions about this? Yeah. So maybe, and that's all. Thanks for your attention, for attending the course.